The goal of the QLink project is to connect quantum processors over really metropolitan distances, to show that a quantum internet can exist outside the lab. Years ago, probably around 2015 or so, we had this vision of connecting multiple cities using a quantum internet. And as a first step, we envisioned we would actually make a link between Delft, where the university is, and The Hague, where the Dutch telecom provider KPN resides.
We're building quantum computers, and we know that these will be part of people's lives in the near future.
There's a worldwide effort going on to realize the future quantum internet. So in the US, in China, Japan, people are trying to establish out of the lab testbeds to really show that quantum entanglement can be used by future customers.
These experiments are very challenging already when you have them in a small lab. But once you start thinking about bringing them into the real world, you have an additional set of challenges that you need to solve. And we couldn't take any shortcuts in this project because we actually wanted to deploy these systems over large distances.
The distance over which we create entanglement in this project, about 10 kilometers, is a world record for the type of entanglement that we make. The type of entanglement between quantum processors.
In order to generate this entanglement, we need to exchange photons between the two quantum computers. And in this project, we do this over 25 kilometers of fiber, while maintaining a phase-stable property of the photons. And this is extremely challenging because that means we need to stabilize the 25 kilometers to 100 nanometers of path length.
We are using qubits and diamonds. And these qubits are special because not only do they allow us to run quantum computations, but they also have an interface to light, to photons. Now what is essential is that with this way we can use exactly the same infrastructure that the internet of today uses, namely optical fibers that are underground connecting the different nodes.
But unfortunately, you can't connect quantum computers over the normal internet that you have right now. You can't go quantum, classical, normal, quantum. You have to go quantum-quantum. And for that, we also have to build a new internet that can support talking of these quantum computers to each other.
If we also have a quantum internet at that point, we are able to connect these quantum computers and let them exchange information and also let them work together, just like we have clusters of classical computers today. There's actually one major difference between the clusters of computers that we have today and the clusters of quantum computers. Namely, the computing power does not scale linearly with the number of qubits, so they don't add up, but they grow exponentially. So two big quantum computers together is much more powerful than each of them separately. With the future quantum internet, we will be able to store and process data in the cloud with complete privacy. And with that I mean that it is impossible for the server to know what data you're putting on the server, what calculation you're doing, and even what data is being sent back. And that's something that is inherently impossible with the internet that we have today. One of the things I really enjoyed in this project is a bike tour that we did, following the exact fiber path between Delft and The Hague. And it's a very weird path because it goes left and right where you don't expect it. You see all these KPN buildings. But most of all, it shows you how large the distance actually is. So to understand that these quantum processors are entangled over such a distance is really amazing if you actually sense it yourself.
So it has been a long road, but we have definitely been able to achieve what we wanted to achieve, which is something that I'm very proud of.
We see that this technology is now ready to be developed commercially going forward.